Okay, it is my very great pleasure to introduce the next speaker in our ongoing online series on gauge-invariant approaches. Today, Lucrezia Ravera will talk about the bundled geometrical relational formulation of quantum mechanics. We are very much looking forward to the talk. Lucrezia, the floor is yours.
Okay, thank you, Philip, for this nice opportunity, and thank you everyone for being here. Let me just make this smaller so that I can see the slides. Okay. So yeah, today I will talk about a bundled geometric relational formulation of quantum mechanics, which is based on this very recent preprint in collaboration with Jordan. And I will start by giving you some motivations. Strictly speaking, under a physical perspective, what we know in theoretical physics, what we apply in theoretical physics in gauge field theory and in general, in general relativistic gauge field theory, is that we try to describe them. They are understood in geometric terms. On the other hand, quantum mechanics is primarily conceived algebraically. And still there is some interest in the geometric structure of quantum mechanics, for instance, in geometric quantization. So here, what I would want to present is a bundled geometric formulation of quantum mechanics, actually more precisely of non-relativistic quantum mechanics. And why so? Because this, first of all, will allow me to show you a generalization of standard bundle geometry, that is Cocyclic bundle geometry, which is interesting on itself, but here will be really the crucial geometric background used to develop this both classical and quantum mechanical bundle geometric framework. And then, because it will be a Lagrangian approach to quantum mechanics, as I will show you in some detail, which resonates in a certain sense with some historical motivation, in particular by Dirac and Feynman, that then brought them to the path integral formulation of quantum mechanics. And moreover, this is the crucial point of my talk. A bundled geometric formulation is a natural environment where to apply the dressing field method of symmetry reduction. And so this will allow for a geometric relational formulation of quantum mechanics. It will be different from Rovelli's relational quantum mechanics, even though it's, as we will see, its interpretation will be in line with it. It also connects with some recent literature on quantum reference frames. And our geometric relational formulation for quantum mechanics is just mathematically closer to what is called geometric quantization. So let me start by giving you an overview of what would be the talk. I will give you some technical background. This is just for actually giving you the key ingredients and the keywords to better understand the logic and the articulation of the talk. So it's not to give all the details and technicalities. The slides are overcomplete in a sense, but we will just see those keywords that are highlighted and will be helpful to follow the logic, in particular regarding first standard bundle geometry, then cocyclic, its a generalization extension that will be useful for the talk in cocyclic bundle geometry, and the dressing field method. Then I will start with a bundle geometric formulation of classical mechanics. So I will consider what I will call the configuration spacetime bundle for a system of n particles, whose base space we will see will be the Newtonian timeline, a universal Newtonian timeline. And we will also see how the gauge group for the structure captures what are called the extended Galilean transformations. And then, so I will first give the kinematics, then I will move on to the dynamics, so mentioning the Lagrangian, the action functional, and I will show how the action functional within this geometric picture induces a flat cocyclic connection, and its associated cocyclic covariant derivative. And this is what will be necessary to then move on to the quantization of this framework, so to a bundled geometric formulation of quantum mechanics. And in particular, we show that the wave functions are objects, simple objects in the framework that are in the kernel of these cocyclic covariant derivative operators, so that fulfill this equation. And when splitting this equation in the bundled geometric framework in bundle coordinates, look at what happens vertically and horizontally, what we will see is that this equation will give us both the prescription of the conjugate momentum operator, and the Schrödinger equation. And I will also mention that having obtained these results, then we can see that the Dirac-Feynman path integral formulation arises quite naturally after having developed this framework. And then I will move on to the core of the talk, that is the relational formulation. And so I will introduce the relational wave functions and Schrödinger equation applying the Dirac-Feynman method. And we will see that the Dirac-Feynman method, by means of those residual symmetries transformations, therefore residual transformation of the second kind, it is able to account for the freedom. There is some ambiguity in the choice of the Dirac field. So accounting for these, we result both at the classical, actually, but in particular at the quantum level, in covariance under change of physical reference frame. And then in the conclusion, I will give you what is essentially the interpretation, the conceptual aspect and interpretation of these results, in particular in the quantum mechanica, under the quantum mechanics perspective. So first, we start with this technical background on standard bundle geometry. So let me just pass through the key objects. We have a principal bundle P that is a manifold of a base manifold M, a smooth manifold M, and it is acted upon the bundle by the structure group H, so as in this picture, on the right conventionally. And then we say that it is foliated under the action of H. It is foliating in orbit under this right action that are called the fibers. Then a mathematical objects say that we introduce for a bundle is we can write what is called the short exact sequence for the bundle, and I'm writing it now here just to highlight because it allows to show which are the key group that act on the bundle. And in particular, we have the automorphism of the bundle that has those transformations that preserve the vibration structure and induce the diffeomorphism on the base manifold. And among these automorphism, we have the vertical automorphism that are those that transform essentially only vertically and induce the identity transformation on M. And then we can write the gauge group for this bundle, whose elements I call gamma. And the gauge group is isomorphic to the group of vertical automorphism. So these, in particular, are the transformation that we will be interested on in the following. Then we have other objects that are relevant on the bundle. They are the differential forms that we can define on the bundle, and consequently the exterior derivative that is the operator that acts on them. And then we can see what happens to this form when we act on them with the right action of H, of the structure group, which defines a property that is called their equivariance. And then we can consider the transformation induced by the group of automorphism, and they are described again on this differential form. They are described via pullback. And the gauge transformations, which are defined in this way, they are so the notation is this for gamma gauge group element. Then by means of the isomorphisms that we have between the gauge group and the group of vertical automorphism can be written in terms of the pullback in this way. So we can classify forms and see that there are forms, differential forms that are particularly relevant in this standard bundle geometric setup, and there are horizontal forms, which are differential forms whose contraction along a vertical vector field is 0. So they are horizontal. Then we have equivariant forms in standard bundle geometry whose equivariance is controlled by the group representation in this way. And then we have tensorial forms that are particularly relevant in physics, as we will see in the following. And they are forms that are both horizontal and equivariant, and they gauge transform in this way. So their gauge transformations are controlled by the representation. Then we have forms that are basic, that are both horizontal, so their contraction along a vertical vector field is 0, and they have trivial equivariance, so they are both horizontal and invariant, and those will be relevant because there are those forms that are produced within the dressing field method by means of the dressing map, as I will recapitulate in a while. So what happens is that the RAM derivative operator does not preserve the space of tensorial forms. And so we introduce a covariant derivative. One can introduce a covariant derivative that preserves this space. And it is defined by means of a connection, which is a principal Hirschman connection that gauge transform in this way, as it is well known for standard bundle geometry and for principal connection in standard bundle geometry. Having seen this, now we can move on to a generalization of standard bundle geometry that is cocyclic bundle geometry or twisted bundle geometry, in which case the equivariance is controlled by a group cocycle C, which is defined in this way. This is the property that a cocycle whose entries are P, so a point of the bundle, and H, has to fulfill for being defined as a group cocycle. And they are essentially generalizations of representations. And then, so these at the group theoretical level, then we can consider the linearization of those cocycle. And I just mentioned them here because I call it A, and it will appear then consequently in the next slide. So I will come back to this anyway. For the moment, just know that it can be linearized. And we can then consider correspondingly the relevant forms in cocyclic bundle geometry that are cocyclic equivariant forms, for which we can see that the equivariance is controlled by the cocycle, rather than by this generalization of representations. Then we have cocyclic tensorial forms, which are, again, horizontal and equivariant with equivariance controlled by the cocycle, and whose gauge transformation, in fact, are written in terms of the cocycle itself in this way. And again, we have that the RAM derivative operator does not preserve the space of cocyclic tensorial forms, and therefore we introduce what is called a cocyclic covariant derivative. In this way, where we can see the appearance of this object, which is a cocyclic connection. How so? Because if we check how it transforms in this way. So again, with the replacement of the representation by means of the gauge group element simply by this cocycle, which takes into account, which takes as entries the gauge group element. And now, with this theoretical background, we can move on to the other piece that is needed, this technical background on the Dirac-Feynman method, and then putting together all of this, we will move on to first to classical bundle geometric mechanics, and then to its quantum counterpart. So regarding the dressing field method, generally we introduce dressing fields which have to have a functional dependence on objects on the bundle. They are defined in this way. The important thing here, okay, K here is a subgroup of the structure group, and this must call K of the gauge group. So it's important to check how dressing field transform under the gauge group to really see if it can be a dressing field. So it has to fulfill this relation. And dressing fields provide bundle coordinatization via physical degrees of freedom, as we will see what it means in the explicit construction I will be showing in a while. So another key object that is necessary to implement the dressing field method is the dressing map, which is defined in this way, maps to P to a subbundle P prime. And it allows to define, for when we have the differential form on the bundle, the dressing map allows to define its dressed counterpart via pullback, and essentially to build basic forms. We can therefore see the dressing of objects that we have already encountered and mentioned before. So the Hirschman connection and standard tensorial form will be dressed in this way, where U is the dressing field. And for the dressing of cocyclic connection and cocyclic tensorial form, we have to take into account the presence of the cocycle, in fact. And here is the explicit way in which this can be written, can be seen. And so we can see, by looking at this expression, we can already see something that is then commonly applied. Once you have understood how to identify a dressing field, then there is a kind of rule of thumb to be applied within the dressing field method to find the dressing of a form. Essentially, we compute the transformation, here K gauge transformation, so the transformation under the gauge group that we have to reduce of a form. And once we have its expression, we substitute the gauge parameter simply with the dressing field to get the dressed K-basic form. Just be careful, this is just a rule of thumb. Actually, it is key, the fact that a dressing field is not an element of the gauge group, and dressed fields are not gauge fixing form. So this was explained in detail in this nice paper by Philip and Jordan. And also we came back to this in a recent paper on generativistic gauge field theory and the dressing field method. So the conceptual core aspect is that this well-defined mathematical prescription to dress forms allow to capture of the dynamical degrees of freedom of a theory, those that are dressed physical relational variables. And so dress forms, we say that they encode the gauge invariant physical relational degrees of freedom among the dynamical degrees of freedom of a theory. We can now see which are those transformations that I mentioned before. In particular, once we dress a form, we can still have, since we can just reduce part of the gauge group, actually, we can have a residual transformation of the, first of all, of the first kind, which are those that are left, that remains the remains of the structure group and gauge groups. To be meaningful, in particular, we have to have the group that has been reduced to be a normal subgroup of the structure group in such a way that we can take the quotient HK, and this will be a group, and it will be essentially the group of residual transformation of the first kind. And then to see how the dressed object transform with respect to this residual symmetry, we just have those of the bare form are known. By construction. We just have to check those to find those of the dressing field, and so we get the whole transformation and the residual transformation of the first kind for the dressed object. Then there are residual transformation of the second kind, which that I was mentioning before. Those are those transformations that encode some possible ambiguity in the choice of dressing field. And in fact, if we consider two dressing fields, they can be related by a group, by a transformation in this way, by an element of this group. And essentially are those transformations under which the bare form is not affected, so it doesn't change. And the transformation affects only the dressing field, so this ambiguity in the choice of dressing field in such a way that the transformation then can be written in this way. And for cocyclic dressing fields, we have the same thing just with the cocycle. So it's just the generalization to the presence of the cocycle. And we will see that those transformations will encode in our framework frame change covariance, both in the classical actually, but in particular in the quantum mechanical case. So we can finally move on to the bundle geometric formulation of classical mechanics. And I introduce this configuration space-time bundle for n particles. So it is a bundle I will mention in a while. It is actually a two vibration, as we can see already in this picture. So it's a bundle over the Newtonian universal timeline. Each point of the bundle corresponds to the instantaneous configuration of the n particles. And it is acted upon by a structure group, which is R3n. So we can write the right action in this way, which is additive abelian, and correspond to the element is this, so it's a shift. And under the right action of the gauge group, we have that essentially each particle position is shifted by a different vector. We can also highlight already this factor, which I will describe more in detail now in a while, that any configuration of particle is actually left invariant by a subgroup of this structure group, which is I denoted here H delta, which is the diagonal subgroup of R3n, so R3, which correspond to shifting all the particles in the configuration by the same shift. So this induces, we can consider a decomposition of H in terms of this normal subgroup and the quotient H over H delta, which is an abelian group. And we have named these two groups H internal and H external. You can see them here represented just graphically. Conceptually and physically, what happens is that H internal implements physical changes in the configuration of particle as seen from any particle within the system itself, while H external only reflects a global change, which can be thought of seen from the viewpoint of an external from an external viewpoint to the configuration itself. So this is a two-fibration structure. And we can see that if we reduce somehow H external, we get a relational configuration space-time bundle, which encodes the internal relative dynamics. So this will be the object that will be interested from now on. Before going to this aspect, let me just mention, as we have seen before, the bundle geometric aspects and the relevant group and forms that we have in general for standard and cocyclic bundle geometry. Of course, they reflect here. We have them here. So we have the automorphism of the automorphism group of the configuration space-time bundle, which induce diffeomorphism on the Newtonian timeline. We have the group of vertical automorphism, which induce the identity transformation on the Newtonian timeline, and then the gauge group, which has this element bold X. I denote them in this way. And the gauge group, in this case, for this system, classical system of n particles, includes the Galilean boost when xt is just v times t. So where v is the constant, is the relative velocity between the configuration p of n particles and an external observer. And more in general, since the elements of H are naturally basic, we can see that the elements of the gauge group depend only on t. And so we can write this expression, which in bundle coordinates essentially reduced to this. And we can see that this encodes what are called in the literature extended Galilean transformations. So again, as we have seen for the structure group, that we have introduced a decomposition of the structure group, and now this reflects on the group of automorphism, in particular on the vertical automorphism and on the gauge group that is isomorphic to the group of vertical automorphism in this way. And again, as we have seen before, cocyclic bundle geometry as an extension, generalization of standard bundle geometry, also here we can consider the cocyclic geometry of the space-time configuration bundle, which is defined via one cocycle that has to take as entries this element X that I introduced before. And correspondingly, we will have a linear Y cocycle at the linearized level. And we can then write for cocyclic tensorial forms and cocyclic tensorial connection the gauge transformation in this way, where X is the gauge group element of the gauge group that we are now considering. So this is, again, the background, the geometric background for this classical space-time configuration bundle. And now we can, this was the kinematics. Now we can start considering the dynamics. So the dynamics of the configuration of n classical particles, we know that it's given by the Lagrangian, which is geometrically, it is a tensorial one form, a cocyclic tensorial one form, as we can see that it transforms with the cocycle. In particular, we can write its gauge transformation in this way. So where this is the cocycle I was mentioning before for the case of the Lagrangian, it can be linearized. And this is what I wanted to mention, is the fact that when we write the linearized transformation for the Lagrangian, so we get the linearized cocycle, this, I will come back to this quickly after, but just to tell you, it encodes the Euler-Lagrange equations of the theory, the cocycle itself, and the details are furnished in our paper. So now that we have this object, there are two main operations that we can consider essentially. One is to take a local section that represents a trajectory, a history in this framework, and then consider the local representative of the Lagrangian on T. So on the Newtonian timeline in bundle coordinates, it can be written via the pullback along this section. And it is this, essentially the Lagrangian density is what in physics we are used to. We are used to see this expression for the Lagrangian. Then in this geometric framework, we can consider, on the other hand, a curve that is a map from an interval in R to the configuration spacetime bundle, which is parameterized by those by tau. And then we can consider the restriction of the Lagrangian on gamma, essentially pull back on gamma in this way, and I call it small l. And what we get is this expression for the Lagrangian density, would be Lagrangian density. In which sense those two objects are different, how they are related? Well, the first one is what we can call the unparameterized version of the Lagrangian, and it's something that we are used to deal with, while this form is, let's say, a parameterized version of the theory, of the Lagrangian theory in terms of tau. And we can see that with the choice t dot equal 1, t dot is the derivative dot, here is the derivative with respect to the tau parameter. So with the choice t dot equal 1, the parameterized version boils down to the unparameterized one. And in particular for x dot, we have that it reduces to x prime, that is the physical measurable velocity for the particle. So we have these two framework at our disposal now. And then again, as we have done for the Lagrangian capital L, also for this small l, we can write the gauge transformation that again is controlled by the cocycle, by a cocycle. It's linearized version that is controlled by the linearized cocycle. And since by using this, just a remark while passing, the fact that gamma dot is right invariant can be used to prove that x prime, so if we compute x dot and this coincides with x prime, this corresponds to a physical velocity shift that is induced by the extended Galilean transformation. Once we have introduced the Lagrangian, we can then introduce the action function, and it's here that we will see how this classical picture actually joins pretty well with can be quantized in a geometric way. So first of all, we define the action functionally as the integral of the Lagrangian over gamma. And this is the parameterized version. By setting t dot equal 1, we get the unparameterized one. Again, if we compute the gauge transformation of the action functional, we can see that it transforms with a cocycle. And then we can compute the linearized version and get the linearized cocycle. And it's here that if we know that the classical dynamics in classical mechanics is defined as the critical points, is here Q's of gamma, so gamma critical. And the classical dynamics is such that the Euler-Lagrange functional for gamma critical is equal to 0. And this here we can prove that this is actually given simply by the vanishing of the linearized cocycle. The details, as I was telling before, can be found in the paper on this aspect, which is nice as a construction by itself. But what I would want to focus now on is the fact that if we now take the action and we see how it transforms, we see how it is defined for gamma critical, it corresponds, we know in classical mechanics that for gamma critical, the action functional can be linked to the Hamilton principal function, which satisfies the Hamilton-Jacobi equation, in which we have here the derivative of the action function with respect to time. And here this is the Hamiltonian, which takes as an entry the derivative of the action function with respect to x, that is the prescription, the definition of the canonical conjugate momenta, which is the conserved nodal charge. And so by looking at how, so the fact that the action function transforms with the cocycle, and then defining a cocycle C in this way, we have that the action functional induces on the space-time configuration bundle a flat cocyclic connection, flat because we take the derivative and it's 0, which is defined in this way. So with the derivative of the action functional in this way. And it also, by means of this, then we can again see the prescription for how to obtain the conserved nodal charges. But then this point is crucial because now we can start thinking of quantum mechanics, because we have, let me just come back to this. So we have this flat cocyclic connection. We can see, we have seen before that when we have a connection, a cocyclic connection, we can write a cocyclic covariant derivative, and then we can consider which are the objects that are acted upon by this Cocyclic covariant derivative. And the simplest object that we can consider is a zero form, a tensorial zero form on the configuration space-time bundle. So this is psi, this is a zero form, is a cocyclic tensorial form, so it transforms this way with the cocycle. And we can consider then its cocyclic covariant derivative, which preserve cocyclic tensoriality, so the space of cocyclic tensorial forms. And now the quantum mechanical statement is the following. So we say that quantum mechanics is encoded in the statement that this psi has to be in the kernel of this covariant derivative. So this will define the space of wave function, and it means that essentially psi, to be called a wave function, has to fulfill this equation, to be a solution of this equation. This is just the way in which this is a subtlety, if we want, how to map from psi associated with gamma critical to a general case, just to have our general framework well defined. And how can we state that quantum mechanics is encoded in this equation? Because if we now take this equation and we develop it in bundle coordinate, we can see that it's split in two contributions, one vertical and one horizontal. The vertical one along the dx give us the kinematical axiom of quantum mechanics, which is the definition of the momentum operator. And on the other hand, along dt, we get the dynamical axiom of quantum mechanics, that is the Schrödinger equation. And let me also mention that now that we have this framework, we can see that if we take psi to be solution of this equation, then we can write psi therefore in this way, and we can write a propagator in this way, where we integrate psi over, this is the measure defined over, it's the integral over all possible gamma with extreme p0, p1. And we get, therefore, that the Dirac-Feynman path integral formulation of quantum mechanics follows in a rather natural way. Now, what we want to obtain is the relational formulation for both the classical and the quantum mechanical framework that we have just introduced, so the geometric framework that we have introduced. Let's see how these apply to the classical framework, first of all, to introduce also the objects that are necessary and how they work. So we have said before that the object that we are interested in is the relational space-time configuration bundle, which was defined in this way. And we can realize it via the dressing field method by reducing, so it's dressing field method of symmetry reduction, in this case, reducing H external. So the external gauge group of the split that we have, of the decomposition that we have introduced before. And essentially by doing so, we can see already graphically say that we will be here essentially. So this will be isomorphic to the relational configuration space-time bundle that we are interested in. And how do we do so? So we need a dressing field, which has to properly transform as a dressing field, and a dressing map whose image will be the subbundle of C isomorphic to C relational. How do we produce such a dressing field for the system of n particles that we are considering? We can see that essentially here I put an index I, because the dressing field will be essentially the minus I, but morally the position will correspond to the position of the ith particle of the system. And correspondingly, we can see in the dressing map that this corresponds to having a 0 in bundle coordinates. So in this point, which is being set in the reference frame is set in the origin with respect to this particle that we are considering as a dressing field. So UI outputs the position of the ith particle of the configuration. By means of the dressing map, we can realize the relational UI, because we have chosen Xi as a dressing field, which is a realization of the relational configuration space-time bundle from the viewpoint of the ith particle. So it is a description of the system from within. Then, as we have mentioned before, once we implement the dressing, we have a residual transformation of the first kind, which are the residual transformation with respect to the dressed, say, internal group. So it is isomorphic to H internal that we had before. It just had an action which is different with respect to the one of H internal, but it is defined in this way, what we obtain. And then we have the residual transformations of the second kind, which encode the physical reference frame covariant. And so, in fact, they encode this the fact that we can choose another particle within the system, the space position of another particle within the system to do the dressing. And so, in this case, we have that this is parameterized by those elements, the ij of this group. And they parameterize a multiple realization of the space-time, of the relational configuration space-time bundle under the perspective, say, of different particles within the same configuration. So it's a switch between internal relational viewpoints. And we can see it if in a rather explicit way, if we consider the dressing map, because we can see that here, this is the origin of the reference system for considering as dressing the ith particle, while here we have this transformation that is relating the xi, xj space, and so the two viewpoints, say. And in fact, if we relate this to the viewpoint, the j's viewpoint to the one of the ith particle, we get this transformation by means of zij, and the origin is shifted to the j's position. And then we can, once we have developed this framework, we have applied the dressing, we can start to dress all the objects that we have defined before, essentially. So we can dress the Q of gamma by means of this composition map, and this will be the relational history of an n particle configuration as seen from an internal viewpoint of any of those particles. And then we can dress the Lagrangian in the same way. So we apply essentially the rule of thumb that we have seen before. So we compute, we have seen before the gauge transformation of this object. Now we just replace with U. And so we get the gauge parameter with U. And we get the dressed Lagrangian one form with the residual transformation of the second kind, which correspond to a shift of a distinct particle in the same configuration for the Lagrangian. Then for the dressed parameterized Lagrangian, we can do the same. And then again, we get a relational Lagrangian as seen from an internal viewpoint of another particle in the same physical history. And we can dress the action. So we, again, as before, we have those residual transformation of the second kind, which encode this ambiguity in the choice of dressing field of particle position. And then having the dress action, we will have the classical relational dynamics as critical points or cures of the dressed action. So this will this leads to what we may call a relational variational principle. Then, as the other objects that we have mentioned before, of course, here they appear again as dressed objects. So we will have the dressed Hamilton principal function, the dressed Hamilton equation, the dressed canonical conjugate momenta, and the Hamiltonian. So those objects that I mentioned before will be just dressed now. And what is important for moving on to the quantum mechanical dressed framework is the dressed flat cocyclic connection. So whose dressing will be written in this way in terms, in fact, as we can see, as the derivative of the dressed action. And it will be subject to residual transformation of the second kinds, which can be written in this way. And again, we can see that this gauge group element, this group relates the relational description of on the relational configuration space by space-time bundle obtained with the dressing UI and the one obtained with the dressing UJ. Now we can therefore consider the psi and the dressed cocyclic covariant derivative, so the psi, the dressed wave function, and we will see in a while how we just dress the equation that encodes quantum mechanics. So we consider the dressing of this cocyclic tensorial zero form, and the dressing of the cocyclic covariant derivative by means of the dressed flat cocyclic connection and dressed psi. And we say, therefore, that our geometric relational quantum mechanics is now encoded in the statement that the dressed object psi U has to be in the kernel of the dressed Cocyclic covariant derivative. And those objects will live in the space of dressed wave function. They will be dressed wave function. And again, if we now take, therefore, this equation and we split it into the vertical and horizontal parts, we will see that we get the relational version of the quantum mechanical prescription of the momentum operator and the dressed Schrödinger equation. So by following the same logic that we have seen before, just for dressed object now. And therefore, in the same way, we can now think of the dressed path integral, so of the relational path integral for psi gamma u, so for dressed objects, solution of this dressed equation, we will get the dressed propagator, so dressed path integral. Coming to the residual transformation of the second kind, and in this geometric relational quantum mechanics description, we can see that, again, also in this case, they encode the physical reference frame covariance. So they are G transformations. Again, they relate the, they encode this ambiguity in the choice of the dressing field. And we can write those transformations for the wave function. So first of all, we write the dressed wave function with respect to uj and by using ui. And so we can see again the shift of the origin and the shift in the entries of the wave function. And then we can see that the shift between a wave function depending on xi dressed in this way and the one dressed with respect to j is encoded into a cocycle, so it's dominated again by the cocycle that is taken as entry this group element that encodes this ambiguity in the dressing. And so we can also notice that the change of physical reference frame is now a unitary transformation of the relational quantum state, of the relational dressed quantum state, which is in fact implemented by the one cocycle C that is U1 value. So it is a unitary transformation of this relational quantum state. So coming to the conclusion, I would want to tell you which are our what we can conclude from those key results, and in terms of possible interpretation of these results. So a first reading of what we got in this, in particular concerning the quantum mechanical framework, actually, so the geometric relational quantum mechanical framework, is that we can say that a reference subsystem, so in this case, with subsystem, reference subsystem, I mean a particle of the configuration of a particle that we are considering, sees itself as a classical. So any other subsystem, so for us, the other n-1 particles are described in a quantum mechanical way from its perspective. So quantum mechanically only from its perspective. And yet, even though we have this, so the particle, the reference particle that sees itself as classical, and only with the other subsystems, we have a quantum mechanical framework that emerges, still we have those residual transformation of the second kind, so the G transformation, which implement a physical reference frame covariance. And therefore, one may say that they ensure a quantum democracy. And what I mean with this, I mean that any subsystem is as legitimate as the other to witness the quantum dynamics. So this is encoded by this physical reference frame covariance and the ambiguity of choosing the dressing field. We can then come to a more refined and accurate understanding and statement, saying that therefore, there is no meaningful way for a given reference subsystem to assign to itself a relational quantum state. This is only possible, it can only do so for other subsystems, and these are which are assigned a wave function with respect to the subsystem itself. So what we have seen as, which is this wave function will be the dressed wave function by means of the subsystem itself, by means of the position of the ith particle of the configuration for us. And therefore, said otherwise, so this final statement is that for a subsystem, for a reference subsystem, here a particle, it only makes sense to assign a quantum state to the set of relations, so therefore this relational framework between itself and the rest of the world. The quantum state itself emerges as a relational object. And then we have this residual transformation of the second kind. So therefore, this physical reference frame covariance, which ensures the equivalence of any of the other subsystem viewpoint to describe this collective relational quantum dynamics. So that's all, and thank you for your attention.
Okay, thank you so much for this great talk. It was really interesting. So now we have enough time for questions. So if you want to raise a question, please, activate your microphone and tell us so, or raise the arm on the Zoom layout. Okay, so maybe I start with something. Okay, Michael, you go first.
Yeah, thank you very much. Since the last slide is here, I think the last slide looks a little bit about the physics. And I mean, vaguely remembering the path integral, I think the issue is that only in very trivial cases like trivial Wiener measures or so you have, or harmonic oscillators, you have the classical path, and then the other ones are nicely symmetric around it and cancel each other out. So you have a clear notion what the classical path is. Later on, if you have more complicated measures and more complicated dynamics, it's not always totally trivial to separate it into subsystems. And I was just wondering, I mean, I understand sort of maybe I totally misunderstand the first reading, that, yeah, I mean, okay, we have a sense of what's the classical path in the path integral. And having the classical one, if we can assign something as classical, then we can sort of see what the other quantum systems. But I wasn't sure about when you wrote the more refined and accurate understanding. Are there these problems with sort of naively classifying these subsets? I mean, there have been recently some debates by Wharton and others on subsystems and path integrals, of course, without any dressing field method. I just want to understand the physics a bit.
I see. No, actually here, okay, this last slide, it comes actually by applying the dressing or whatever. Anyway, coming to a relational description of it via dressing, we see that what we get is that in general, within this geometric framework, but in general is an interpretation, we cannot say that a particle itself or a subsystem itself can be seen itself as quantum on its own. It doesn't make sense. And so the second refined statement is just actually a rephrasing of the first one in better terms. And so the subsystem itself sees itself as classical, but the quantum aspects, the quantum state emerge in a relational way. So in relation with the other, this is where quantum mechanics come into play. And these, okay, we didn't dig into the path integral formulation actually with our method. We are about to do that, but here the construction was regarding the rest of essentially how to derive the Schrödinger equation and the prescription for the. But still, yeah, it should apply anyway. This interpretation is actually goes beyond the approach that then one decides to follow to quantum mechanics. So if a geometric quantization, if path integral is whatever, it's just an interpretation that we obtain from the physics, from the mathematics, and from the physics, from the geometry, that tells us that this has to be the case. So that it seems that really talking about quantum means talking about rationality. Yeah.
Okay, perfect.
Sorry, because you defined an action, that's why I thought you were going that way already. Path integral.
No, I use the action. I define the action because it is important. It is the key object that I use then to define the flat from the way in which the action transform in this geometric setup. Then I define so with the cocycle that I defined before. Then I define a cocycle, and I see that in this way I can assign the action functional itself, its derivative actually, induce a flat cocyclic connection. And so I use this object to define a cocyclic covariant derivative, and this yields, looking at the in-bundle coordinate, yields the prescription for the canonical momenta. In quantum mechanics, the canonical the momentum operator and the Schrödinger equation. Yeah.
Okay. So for me, what I'm wondering about, what I'm interested in, is the big picture in which this work is embedded. So maybe for me it is most helpful, and if it's okay for you, I just say stuff, right? I just talk something, and you interrupt me as soon as I say anything that you disagree with. Okay, so it turns out, right, our best physical theories are gauge theories. There's some agreement that gauge theories are best formulated mathematically on a basic level in terms of fiber bundles, in terms of bundle geometry. It turns out that this works very well at the classic level, right? For the addressing field method, which is hopefully a good and insightful way to reduce gauge symmetries, is best and most accurately described in terms of fiber bundles. And this works very well on the classic level, in the classic realm. There's not so much work done on this on, let's say, relativistic quantum field theories. And now when you do this in, or let's say in relativistic quantum field theories, and let's say quantum electrodynamics and so on, blah, blah, blah. And now when you provide this formulation of non-relativistic quantum mechanics, is this supposed to be a step towards a fully relativistic reformulation?
Yeah, absolutely.
Okay.
Yes, this is just the beginning. Is a step for a huge program, and a step for that also within itself. So within this sector that you are talking about, yes, essentially first, this is just for any particle configuration. Particles that don't have internal structures, somehow they didn't. So one could also consider them generalized to rotations and so on. So complicate the system in this direction. And also, this is non-relativistic, where one could consider relativistic and so on. So this is a part of our future program. Yeah, absolutely.
And in this paper and in this work, in this talk, the aim is not to provide, I don't know, a new interpretation of quantum mechanics, or I don't know, a new twist on this, but it's just basically a reformulation of the formalism, right? So you want to reformulate the formalism of quantum mechanics in terms of bundle geometry.
Exactly.
And even to the extent that you are able to identify a principal bundle of the theory, right? So the principal bundle now becomes your configuration space time.
Yeah.
Okay.
Exactly.
Does this mean now that quantum mechanics is a gauge theory with the principal bundle being the configuration space time and so on? I don't know.
Well, in a sense, formulated in this way, well, we apply the machinery, a machinery that is known, that is commonly applied to gauge field theory. So here we are not actually yet introducing probably what would one would call in a field theoretic framework fields. But yes, we are applying the machinery in a kind of similar way. We have gauge group, we see how it acts. Here is slightly different because, for instance, commonly in gauge field theory, the gauge transformation is this thing that they don't reflect physical change of a system, transformation of a system. And here they actually do. So there are subtleties, there are differences, but we are essentially applying the bundle geometric setup to quantum mechanics, see what happens. So from and also because to also see which are the analogy that we can in fact that we can obtain with field theory. So in a sense, a further step that we are now working on is actually concerning exactly this point of applying this geometric setup to, in a more field theoretic way, say, to this framework, to standard physics that is not commonly conceived as a gauge field theory. So yeah.
Okay.
And also in this way, we not only we get this nice geometric picture, so which is useful by itself to deal. You start seeing more of the physics by means of the geometry, because you push the geometric framework as much as you can. And then you can see that, when, especially in going relational and doing regressing, you start seeing that an interpretation also emerge. You can see that you understand that a particle sees itself as classical and the quantum state itself emerge in a relational way. So it also tells you something, just this, that is in this concluding slides at the moment, but about the interpretation of the physics and of the mathematics.
Okay, wonderful. And maybe just to remind this or to illustrate this regarding the principal fiber bundle, maybe you could show us again slide 17. I think it was slide 17 for the first time.
Okay, tell me where to stop because I don't know.
I think it says, when it says page 17 on top of this. So just
I
go
cannot
on.
see the page. Okay, so I go on.
So now we're on 25, 24. So now it should be, oh, no, in the other direction now. I think
the
6
first
times in the
picture
other
of the
direction.
bundle.
Is the picture of the configuration spacetime bundle?
This one, yeah.
This is not the dress. Okay. Okay.
So here, so here we have the bundle. And this is, as a matter of fact, the principal bundle, right? The configuration spacetime is supposed to be a principal bundle, which means that the structure group is the typical fiber, right, of the fiber bundle.
Yeah.
Okay.
The only thing is that here we have this decomposition. It is a two fibration because we have this and this. So this decomposition with H external and H internal. H external is just the diagonal group of R3n, which is the whole H. And so here is already shown in a decomposed way, say, so to better show this two fibration structure graphically.
I mean, it sounds, it looks really interesting. It looks really nice that you have a space Newtonian universal time, and then for each point in time you have the configuration space time. Okay. This is very interesting. And then when you talked about the interpretation of quantum mechanics, or when you say, okay, you do this, you put forward a reformulation of the formulas in terms of fiber bundles, and then maybe this tells you something about how to understand quantum mechanics, right? What I'm wondering about is, so I mean, obviously, right, I'm on your side, so to speak, and I'm in favor of doing it with respect to dressing field method, right? And then you say that you come up with the rest Lagrangian and so on. But if you are not prima facie interested, right, in the dressing field method or in dressings, what benefit do you get from moving from the just normal fiber bundle formulation of quantum mechanics to the dressed formulation? So why would you do this if you're just interested in formulating it in fiber bundles? What does it help you? What does it give you? What is the additional virtue of doing it with the dressed Lagrangian or the dressed the theory, so to speak?
Yeah, actually, just starting, so already at the classical level, this I find this geometric description of the configuration spacetime bundle particularly nice because let me just see if I can come to the slide that I want. Okay, because all the objects that we know that we almost daily deal with in physics essentially here emerge in a geometric way. And if you push this geometry and you define, so for instance, first you study the kinematics, then you write the dynamics, and you define the action. And already here you can see these objects or these equations that we commonly deal with. We know these things, but emerging geometrically. And if you, already the classical level, these like the Hamiltonian, the Hamilton-Jacobi equation, the canonical momenta, and so on. And then once you have this, you just consider, you consider cocyclic bundle geometry, so this generalization of bundle geometry. And you see that from the way in which the action transforms, you can introduce this flat cocyclic connection. And this is key, I think, because from this geometric picture, you already have this object. And so you notice that once you have a connection, which is, in fact, this flat cocyclic connection, you can introduce, you're then left to introduce the cocyclic covariant derivative. And in this way, you are immediately led to think of also the, I don't know how to say, how the quantization of this framework seems to emerge in a natural geometric way, because you have the connection, you define objects that you define therefore the cocyclic covariant derivative. You think of object on which this operator acts. The simplest is a tensorial cocyclic zero form, and by simply looking at the kernel of this operator, you get the quantum dynamics. So the kinematic actions, the kinematic action, the momentum operator, and the Schrödinger equation. So without thinking of the dressing, this is just not even operationality, it's just classical and quantum mechanics emerging in a geometric way, and it's powerful by itself, I would say.
Mm-hmm.
And then while regarding the interpretation, so also the conclusions slide that I was showing you and so on, there you see that once you have these, all of this, then you can dress it. Being geometrical, the framework allows to apply the dressing field method in a nice way. And therefore there you see that the definition of quantum state itself has to be relational. And so, okay, this I would say that you develop this geometric framework, but then if you can dress it, because it will show you really the physics and the interpretation, we really understand what's happening physically.
Mm-hmm, mm-hmm. So since on the slide you have the dynamics, right? You have the dynamical axiom, you have the Schrödinger equation, then I guess reformulated in your formulation. So in textbook quantum mechanics, or in typical textbook quantum mechanics, the dynamics of quantum mechanics is not limited to the Schrödinger equation, right? Unfortunately, one would say, because okay, the wave function evolves according to the Schrödinger equation unless a measurement takes place, right? And then when a measurement takes place, you have the collapse postulate, right? So you have basically two dynamics. You have the Schrödinger dynamics and you have the collapse postulate. So if I understand you correctly, you would say you only need the Schrödinger dynamics?
No, well, okay. Yeah, it's unitary and non-unitary dynamics, and yes, I agree. There is also this the collapse of the wave function. I'm not saying that we need only the Schrödinger equation. We didn't just analyze the collapse of the wave function yet. That is actually the point.
Okay.
Yeah.
Because in relational quantum mechanics, right, in the spirit of Rovelli, it's not the same as in textbook quantum mechanics, right? So in textbook quantum mechanics, you really have, in the Copenhagen interpretation, you really have these two dynamics. But I think in relational quantum mechanics with Rovelli, it's a bit more subtle, I guess. I don't know. So I think for Rovelli, the collapse of the wave function is not something basic, not something fundamental as in textbook quantum mechanics, but it's, you know, I don't know, a side effect of a perspectival understanding of it. So the wave function does not, you know, universally, objectively represent the state of the universe, but it's perspectival, and then for some observer, for some reference frame, the wave function has collapsed, but for another one it has not collapsed. And then I guess, but I'm not an expert in this, I guess in the context of relational quantum mechanics, in the spirit of Rovelli, one would say, yes, the basic dynamics really is the Schrödinger equation. And then with respect to the collapse, we have to tell a more subtle, perhaps perspectival philosophical story. And I thought that maybe your approach goes in this direction, but I guess that maybe you want to stay neutral on this and just see what happens when you formalize this part of the formalism.
Yeah, I would say that from the last thing also that I showed you in the conclusion, in a sense, it may go in this direction. So in, I don't know, re-evaluating in a sense maybe the collapse of the wave function, yes, but yeah, we will analyze it apart, because yeah, at the moment I don't have a strong position yet, but still since it's a relational, so it's mathematically very powerful, this approach, then the geometric approach to this relational, so this geometrical relational quantum mechanics. it's relational, so I would expect something to be shared also, because the interpretation is still in line with the Rovelli's one here. So maybe yes, but we will see in the near future, or hopefully if it goes the same way.
Perfect.
Maybe Philip, I can add something to that with just to because indeed, as a matter of fact, we did not really think much yet on the collapse postulate, but because there is two things at least that is often repeated by Rovelli in his writing around relational quantum mechanics, is that, well, first, he doesn't endorse an ontological view of the wave function. And for that, he says, if you look at the semi-classical approximation, you see that the wave function is somewhat the exponential of the action, and we don't take a strong ontological position for the action itself. Or he says Hamiltonian, maybe something like that. And in the geometrical framework, as Lucrezia just showed it's exactly like that. That we really see that the wave function is solution of sort of a parallel transport equation, and therefore becomes a kind of a solution is just exponential of the action, essentially. So on that front, we kind of agree with Rovelli has a point, you could say, on that front. So maybe it gives the geometric framework gives a good reason to be careful where you want to put your ontology, so to speak. So psi, the wave function doesn't have to be invested with a big heavy ontological weight. And as Lucrezia has been explaining in her last slide, the one thing in which we certainly converge with relational quantum mechanics à la Rovelli is the notion that what emerged, and maybe it goes back to your question before, is that what is gained by by addressing the whole geometric framework is that you see very explicitly that there is no meaning in saying that a particle has a quantum state. A particle doesn't have a quantum state. It's what has a quantum state is the relation between two particles, or rather, generally, or you can generalize the statement by saying a system doesn't have a quantum state. It's always the relation of a system with another that is given a quantum state. And I think that is somehow one of the pivotal insights of the relational interpretation. And in the Rovellian way of thinking, you have to maybe ponder much about this, to convince yourself of this, to thinking much about the quantum mechanics, the formalism and stuff. In the way in which it is done here geometrically, it becomes obvious. So you don't have to be smart in a sense, to zero in on that insight, because the mathematics give it to you, essentially, or strongly hints at that interpretation, at least. So that's the two things maybe in which we converge with the relational quantum mechanics stuff. But you're right, as Lucrezia says, the collapse itself, we did not yet really thought deeply about it.
Okay. I would have one final, I don't know, question or comment on the distinction between residual symmetries or transformations of the first and second kind. So I think this was first mentioned on page 16 on your slides, so very early.
Yes, so before this, essentially.
Yeah, this
yes.
one. Okay. So to some extent, right, residual transformations of the first kind or residual symmetries of the first kind, they're quite straightforward, right? So if you don't remove the full gauge symmetries with the dressings, then you have these residual transformations of the first kind. Is this correct? Okay. Then, as you say, the transformations of the second kind, the residual transformations or residual symmetry of the second kind, they're somehow connected to the choice of the dressing field. And I mean, as you know, this is something that, you and I think that this is quite interesting, right? Because when we think about gauge fixing, for instance, typically we would say gauge fixing is a bit arbitrary, right? So there are different ways to gauge fix. And why should we then say that this particular way of gauge fixing somehow reveals a deeper ontology or whatever? But then, of course, the counter argument would be, okay, but if this if there's this kind of ambiguity also in the case of the dressing field method, in the case of dressings, isn't it quite similar, right? So you could dress up the gauge field or whatever in various manners. You make a choice, you dress it up in this way, and then obviously, yeah, this will not reveal the deep ontology necessary if there is this ambiguity and if there are these different ways of dressings. So when I have talked about this with Jordan, it has come up that in particular scenarios, in particular cases, the choice of the dressing field is limited, right? So that there are not infinitely many choices or whatever, but that you have, for instance, a discrete symmetry or discrete transformation, maybe even a unique one. So is this something, do you think that digging deeper into these transformations of the second kind and this symmetry of the second kind, and then limiting this, that this could help us to reveal something like a deep ontology, that it goes beyond, then when we would not do this?
Well, a deep ontology, I'm not sure. Well, what I can see here already in the framework and the kind of systems that we have just seen now is actually that, it is, first of all, it is one of those cases in which the group, in fact, is discrete, this group of residual transformation of the second kind. So it reflects the ambiguity of choice of dressing within the configuration, the end particle configuration. So it is discrete and it corresponds to choosing different particles position to dress. But and already at this level, we see that it encodes within. So having described the system of classical and quantum particles geometrically in this way, and considering the residual transformation of the second kind after applying the dressing, it reflects physical frame change covariance. So it is telling us something important. And in the end, moving on to the quantum mechanical framework, it shows us that we have a quantum, what we are called a kind of quantum democracy. So we have a relational picture in which we see that the particle see itself as classical, not as quantum, and quantum state is defined only relationally. So with respect to the other system, the relation between the other systems, but still we have this residual transformation of the second kind, this residual group transformation that encodes physical reference frame covariance, quantum democracy, meaning that each of these subsystems is equivalent for as equally legitimate to describe these quantum relational dynamics from within with respect to the other system. So here it is encoding something important, and I don't know if this replies to your question regarding the.
Okay, I mean, maybe I guess it does. But just to be sure, so with respect to the first kind, right, with respect to residual symmetries of the first kind, it is in principle possible to totally remove them, right? It should be possible via dressing in certain scenarios that there is just no residual symmetry, residual transformations of this kind.
If you dress with respect to the whole structure gauge group, yes. In principle, yes, it will be object invariant under the whole social group,
And with respect to the transformations or symmetries of the second kind, is it also possible in certain scenarios you could fully remove them so that you then have a unique dressing?
I'm not sure. I would say, well, it depends. If you don't have the ambiguity in the dressing, you don't see them. But if you can have more than an object that you can promote, I mean, that you can select as a dressing field, then you will have this residual symmetry, and it will encode something that is not actually physically relevant. It's maybe an internal residual symmetry, but it will tell you something important as a principle, in a sense, to be respected for consistency of the framework, and so it will tell you something about the physics. In this case, is this frame covariance, and I wouldn't say that in general, if in general terms, so if you have more than one dressing at disposal, you will still have these residual symmetries.
Okay, thank you so much. Okay, do we have further questions? Because if not, then I will stop the recording.